Welcome to the deep dive. It's late. The glow of your monitor is probably the only light in the room right now, and, well, if you're tuning in, it means you're a software engineer ready to level up your mental models around AI.
Yeah, you already know how to write code, manage databases, architect systems.
Right, but today we're looking under the hood of the systems that are actively reshaping our industry. We're pulling from some really fantastic source notes on the LLM Mastery module regarding the transformer.
And our mission today is to unpack a concept that sounds, deceptively simple on paper, just run attention multiple times. But it fundamentally changes how large language models actually process and understand data. We are talking about multi-head attention.
Okay, let's unpack this. We covered standard self-attention previously, where tokens generate queries, keys, and values to figure out what other parts of a sequence matter.
Right.
But the source material insists that a single attention mechanism is, well, it's insufficient. Why? Is one attention pattern, one lens, not enough to process language?
It really comes down to the sheer density of human communication. A single lens mathematically and practically forces the model into a severe compromise.
Okay.
To see why, let's look at the seemingly simple sentence from our source material. The bank approved the loan after reviewing the application. When you read that sentence, your human brain fires on, multiple cylinders simultaneously.
Because I'm tracking the basic syntax.
Exactly. Identifying that bank is the subject and approved is the verb. But you aren't just doing grammar. You're parsing semantics. You immediately understand from the context of loan that this is a financial bank.
Not a grassy riverbank.
Right.
And there's also the core reference resolution happening in the background.
Yeah.
When I read the application, I intuitively map that back to the loan application mentioned earlier.
Right, rather than assuming someone is talking about a software app on their phone.
Yeah. Plus, I'm registering sentiment, and approval is a positive outcome. I'm mapping all these distinct relationship patterns at the exact same time.
And that simultaneous mapping is the core problem for a single attention mechanism. If you only have one attention head, you are forcing the neural network to cram all of those distinct relationships.
The grammar, the meaning, the sentiment.
Into a single set of attention weights. It becomes a mathematical bottleneck. The model has to average out its focus. It's kind of like asking one single person on your engineering team to simultaneously be the hardcore backend systems architect, the front-end UI designer, the database admin, and the QA tester.
They might keep the app running, but they're going to do a pretty mediocre job at everything because their focus is just split in too many incompatible directions.
Exactly.
The source material uses a really helpful analogy for this. They compare the ideal state to a newspaper editorial team. Rather than having one overworked editor reading a manuscript and trying to catch absolutely everything, you hand the exact same article to a team of specialized editors.
Who are all hunting for completely different things.
Right.
You'd have a grammar editor who is solely focused on subject-verb agreement, meaning editor checking if the logical flow makes sense. A style editor looking at tone. A fact-checking editor running the numbers.
And a references editor making sure all the pronouns actually point to the correct antecedents.
Exactly. Each of those editors makes their own specific notes. In the architecture of the model, those notes are the attention weights. They are looking at the exact same input data, the exact same sequence of tokens, but they're producing vastly different analytical outputs based on their specialization.
And then they sit around a table, combine all those notes, and synthesize them into one rich, comprehensive review. That is what multi-head attention is doing. It gives the model a team of specialists.
Yeah.
But from a systems architecture standpoint, how are we building this without destroying our compute budget? Because my first instinct as an engineer is, well, if I need 8 editors, I'll just run the full attention algorithm 8 separate times. But structurally, that sounds wildly inefficient.
Oh, running full attention 8 times over would absolutely obliterate your compute budget. To engineer this efficiently, we have to look at the tensor shapes and the dimensions.
Okay, lay it out.
Let's say your model has an overall embedding dimension, what they call D model of 512, and you decide you want your architecture to have 8 attention heads. Instead of duplicating the 512-dimensional space 8 times, you split it.
You take that 512-dimensional space and divide it by the number of heads.
Oh, right.
So 512 divided by 8 gives us 64. That 64 is our head dimension, or DK.
Exactly that. What happens next in the computation pipeline is that for each of the 8 heads, the model instantiates separate, unique weight matrices, the WQ, WK, and WE matrices.
But here's the critical optimization. These matrices are not projecting the input into another massive 512-dimensional space?
No, they're projecting the 5 to 12-dimensional input down into their own specific 64-dimensional subspace.
It's like cutting a pizza.
When you need to feed 8 people, you don't order 8 massive, separate 512-dimensional pizzas. You take your one 512-dimensional pizza and you slice it into 8 equal pieces of 64 dimensions.
I love that. You are parallelizing the memory allocation. You give each head a smaller slice to work with, but grant them the total mathematical freedom to find their own unique patterns within that slice. The total volume of computation remains roughly the same as if you ran one giant attention block.
Let's trace that computation pipeline for just one of those slices. Each head takes its 64-dimensional slice of the data and independently computes self-attention.
Right, it takes its 64-dimensional queries and calculates the dot product with the transposed keys. It scales that result down to prevent the gradients from vanishing, applies a softmax function to turn the raw scores into a probability distribution.
And then multiplies that distribution by its values. The output from that single head is a 64-dimensional vector for every single token in your sequence.
Exactly. And all 8 heads are executing this exact same tensor math at the exact same time across your GPU cores, completely independently.
Wait, if you just concatenate 8 separate 64-dimensional vectors, they haven't actually shared any information.
Yeah.
You just have 512 dimensions of siloed data sitting next to each other.
True.
How does the model actually synthesize that so the next layer of the neural network can use it?
Cue the editorial meeting. The concatenation gets you back to your original 512 dimensions, but you are completely correct that the 8 streams haven't talked to each other yet.
Right.
To synthesize the data, you pass that concatenated 512-dimensional vector through one final linear projection. This is the output projection matrix, or WO. This matrix is learned during training, and its entire computational job is to figure out how to best mix and merge the insights from all 8 independent heads into a single, cohesive 512-dimensional output.
It weighs the importance of the grammar editor's notes against the coreference editor's notes.
Blending them all together,
Yeah.
exactly.
Here's where it gets really interesting. Think about this from a programming perspective. If I'm writing traditional logic to parse language, I hardcode a regex for punctuation, or I write a deterministic function for subject-verb agreement. In this architecture, how do we assign these editor roles?
You don't.
Right, how does the model know that head 1 needs to be the grammar head and head 2 needs to be the coreference head?
Nobody programs them to do anything specific. It is entirely organic. It's emergent specialization driven purely by gradient descent.
The model just starts with completely random weights in all of its matrices.
Exactly. During the training phase, it tries to predict the next word, inevitably makes a mistake, calculates the loss, and backpropagates that error through the network. Over billions of iterations, the calculus of gradient descent naturally pushes the weight matrices of the different heads away from each other in the latent space.
It forces them to capture different types of relationships simply because that is the most mathematically efficient way to minimize the training loss.
The team of editors forms spontaneously.
That is fascinating. The source notes mention that researchers have actually gone into the latent space and visualized what these trained heads are doing. When they dissect them, the patterns they find are incredibly specific.
Yeah, they found syntactic heads that light up specifically to connect subjects to verbs or adjectives to the nouns they modify. They statistically learned grammar without a rule book.
You also see positional heads.
Right.
These are heads that completely ignore the semantic meaning of the tokens and act like strict Bigram trackers.
Yeah.
They dedicate their entire slice of the compute purely to tracking local sequential structure, always paying attention to the token immediately preceding the current one, or 2 tokens back.
And then there are the coreference heads. Coreference resolution, figuring out that the pronoun she refers to, the lead engineer mentioned 3 paragraphs ago, that used to be a notoriously brittle, incredibly difficult problem in traditional NLP pipelines.
Oh, absolutely.
But here, a specific attention head just naturally assumes that responsibility. Whenever it sees a pronoun, its attention weights spike on the correct antecedent.
There are even rare pattern heads, tracking punctuation structures or mapping semantic fields. A head might light up when the words doctor, hospital, and patient appear in the same context, mapping the conceptual territory of healthcare.
What's fascinating here is the philosophical shift in how we process information. You might ask, Why is an architecture of 8 heads of 64 dimensions so much more powerful than one head of 512 dimensions?
Right, because the total number of parameters is essentially identical.
The compute cost on the GPU is roughly the same, so why parallelize?
I assume it comes down to representational diversity.
Think of it like an investment portfolio. If you have $100,000 and you put it all into one single tech stock, your entire financial future is bottlenecked by the dynamics of that one company.
A massive, fragile compromise.
But if you diversify, if you split that money across 8 different stocks in different sectors, your portfolio captures a much broader, more robust set of market dynamics. Multi-head attention is mathematical diversification. It gives the model multiple independent votes on what matters in the sequence.
It's like binocular vision. If you cover one eye, you still see the entire room, but your depth perception flattens out. You lose the 3D richness of the environment.
Yes.
Now imagine having 8 eyes, or 64 eyes, all viewing the exact same data from slightly different mathematical angles. When the output projection matrix synthesizes all those viewpoints, it creates a high-dimensional depth perception that a single lens could never achieve.
This is why, as models have scaled up over the years, the number of heads has scaled right alongside them. The original transformer architecture from 2017 used 8 heads.
Right.
By the time we got to BERT Large, it was 16 heads. GPT-3 pushed it to 96 heads with 128 dimensions per head. LLM 7DB uses 64 heads. The trend in the industry is clear. More heads equal more perspectives, and larger head dimensions give each perspective more expressive power.
But scaling like this has to hit a hardware wall eventually, right? Because while the training phase is highly parallelized across massive compute clusters, inference actually running the model to generate text for a user forces us to confront the physical reality of hardware memory.
This is where the theoretical math hits the silicon. We know self-attention has a big O of n-squared complexity, where n is a number of tokens in your sequence or your context window.
Right.
During inference, when you are generating tokens one by one, you have to remember the context of everything you've already processed. To avoid recalculating everything from scratch for every new word, the architecture stores the key and value vectors for all previous tokens across all your attention heads. This mechanism is called the KV cache.
The KV cache. If you are an engineer working with large language models, this is the beast you spend all your time trying to tame. Let's make this tangible with some back-of-the-napkin math. The source notes highlight a staggering metric.
Let's hear it.
If you have a modern model with 64 heads, and you pass it a 100,000 token context window, which is common now for analyzing massive code bases or entire books, the memory consumption is wild.
Let's break that math down. For every single token, you have to store a key vector and a value vector. If your head dimension is 128, that's 256 floating point numbers per token per head. Multiply that by 64 heads, multiply that by 100,000 tokens.
Okay.
If you are using 16-bit precision, which is 2 bytes per float, you are suddenly looking at tens of gigabytes of GPU VRAM consumed entirely by the KV cache.
Just to store the context of a single user's prompt.
Exactly.
So it becomes a memory-bound problem rather than a compute-bound problem.
Yeah.
Your GPU cores are incredibly fast, but they're just sitting idle waiting for gigabytes of key and value tensors to be fetched from memory. If the KV cache is hogging all the VRAM and throttling the memory bandwidth, how are engineers bypassing that bottleneck?
They hack the architecture. The first major breakthrough in solving this was multi-query attention, or MQA. The fundamental realization was that the model's expressive power comes primarily from having unique queries. So instead of giving every single head its own unique key and value matrices, MQA forces all 64 heads to share the exact same key and value matrices. They only keep their unique query matrices.
Going back to our newspaper analogy, that's like having 64 editors who share one physical copy of a reference book rather than buying 64 individual copies.
That's a great way to put it.
The reference book itself, the keys and values, doesn't change. But every editor approaches that shared book with their own unique set of questions, their queries.
From a systems engineering perspective, MQA is a lifesaver. By sharing the keys and values across all heads, your KV cache shrinks by a factor of your head count. In a 64-head model, you just reduced your memory overhead by a factor of 64. You go from needing 32 gigabytes of VRAM, just for context, down to half a gigabyte. And the shocking part of the research is that the drop in generation quality is minimal. The diversity of the unique queries does most of the heavy lifting.
But MQA can sometimes be a little too aggressive on the compression, losing just a bit too much nuance in highly complex reasoning tasks.
Which brings us to the modern gold standard mentioned in the notes, grouped query attention, or GQA.
GQA sits right between the massive memory footprint of full multi-head attention and the aggressive compression of MQA. Instead of every head having its own KV or all heads sharing one single KV, you group them.
Right?
Let's look at Meta's LLM 270B as the perfect case study. It has 64 query heads, but instead of 64 KV heads or just one KV head, it uses 8 KV heads. It creates 8 groups where 8 query heads share a single KV pair.
It's like restructuring the newspaper into 8 distinct editorial departments.
Yeah.
Inside the science department, you have 8 different editors all sharing the same science reference materials.
Yeah.
Inside the sports department, 8 editors share the sports references.
Yeah.
They share resources locally to save budget, or in our case, VRAM. But you still maintain distinct pools of reference material across the whole organization. Llama uses this to dramatically speed up inference and save gigabytes of memory while keeping the output quality virtually indistinguishable from a full, unoptimized multi-head setup.
It is a phenomenal piece of engineering. But looking at these optimizations raises an interesting question about architectural redundancy. We are building these massive 64-head models and then forcing them to share resources. Do we actually need all 64 heads to begin with?
That's a great point. If they're sharing resources anyway, are some of these heads just sitting around drinking coffee in the break room while the syntactic and coreference heads do all the actual work?
If we connect this to the bigger picture of deep learning theory, there's a fascinating concept called the lottery ticket hypothesis. The theory states that when you train a massive, overparameterized neural network, the entire network isn't actually doing the heavy lifting. Hidden inside that massive architecture is a smaller, leaner subnetwork, a winning lottery ticket that happened to initialize with the right weights and learn the optimal features.
And the rest of the network is essentially dead weight.
Pretty much.
And we see this explicitly with attention heads. The source notes highlight research showing that you can take a fully trained model and literally just delete 20 to 40% of the attention heads, and the model's benchmark performance barely twitches.
You do have to be careful with pruning. Some heads are critical load-bearing pillars. If you delete the syntactic head-handling subject-verb agreement, the model's language generation completely collapses. It causes catastrophic failure.
Sure.
But there are dozens of other heads that, during the billions of training iterations, just never found a useful pattern in the latent space. They are mathematically inert.
For the engineers listening, understanding this pruning concept is huge if you are trying to deploy AI to the edge. If you want to run a model locally on a mobile phone or a low-power IoT device, you don't need to load a 100-gigabyte behemoth into memory. You can take a massive model, analyze the attention heads, identify the 40% that didn't find a winning lottery ticket, prune them out, and ship a tiny lightning-fast model that retains almost all the core capabilities of the original.
Exactly.
But that begs the question, why build them so big in the first place? Why burn millions of dollars training 64 heads if we only actually need 40?
Because the model doesn't know in advance what it's going to need. Training is fundamentally an act of exploration. You give the architecture an excessive capacity and excessive heads, so it has the sheer computational surface area to freely explore the data landscape.
The redundancy isn't a bug.
No, it's just the necessary price you pay during the training phase to discover the optimal specialized features. Once you found them, you can prune the excess for inference.
And it's an architecture that translates everywhere. We've been talking entirely about language words, sentences, syntax, but multi-head attention is practically a universal computational primitive at this point.
Oh, absolutely.
If you look at vision transformers, or VITs, they do the exact same thing to images. They chop an image into patches, and the multi-head attention lets each patch attend to every other patch. You get one head specializing in edge detection, another looking at textures, another mapping spatial relationships.
You see it in biology, too. AlphaFold revolutionized protein structure prediction using this exact mechanism. It processes amino acid sequences, and the different attention heads organically learn to track evolutionary relationships, physical proximity in 3D space, and chemical bonds.
Because a protein folding isn't just driven by one physical force.
Exactly. It's the interplay of dozens of forces, which makes it perfect for multi-head parallelization.
Even in music generation. You have heads tracking the melody, heads tracking the underlying harmonic structures, heads managing the rhythm, text, images, proteins, music. The underlying principle is perfectly universal. You take complex data, you spin up multiple independent perspectives, let them specialize through gradient descent, and synthesize their outputs.
Yeah.
So what does this all mean for you, the engineer?
It means when you are looking at a large language model, you shouldn't just see a black box of magic math. You are looking at parallelized computational streams. By understanding that the embedding dimension is physically sliced across these heads, you have the mental model to understand why memory bandwidth becomes your enemy during inference.
Spot on.
You understand why managing the KV cache is the most critical part of scaling your application, and why architectural optimizations like grouped query attention in models like Llama are absolute game changers for your deployment costs.
It completely demystifies the system. But I want to leave you with something to ponder, a bit of a puzzle that the source notes hint at. We've just spent this entire deep dive talking about how these brilliant, specialized heads look at all the words simultaneously to map out grammatical and semantic relationships. It is, at its core, parallel matrix math.
Right.
But wait, if it all happens in parallel, if all the matrices are multiplied at the exact same time across the GPU cores, how does the model actually know the order of the words?
Oh, that is a great point. If everything is processed at once, sequence goes right out the window.
Mathematically, pure self-attention treats language like a scrambled bag of words. Dog bites man and man bites dog look exactly the same to the raw attention mechanism because the dot products compute the exact same way regardless of the sequence they are fed in.
Fascinating.
So as a systems engineer, how would you mathematically inject the concept of time or sequence into pure, unordered, parallel matrix math? That is a fundamental constraint of this architecture, and it's something to chew on before we dive into positional encoding next time.
A perfect cliffhanger for the architecture geeks. Thank you for tuning into the deep dive. Keep optimizing, keep building, and we'll catch you on the next one. Have a great night.